So we're going to talk about the relationship between the derivative of a function and the derivative of an inverse. So let's revisit pre-cal. In pre-cal, we discovered that a function g is the inverse of a function f if and only if the following is true. If f of g of x is equal to x and g of f of x is equal to x. So that has to be true for every value of x in the domain of g and every value of x in the domain of f. So a classic pair of inverses that we learn are in fact y equals e to the x and the function y equals the natural log of x. And they're inverses because they are reflections over the line y equals x, except I probably should have drawn them a little bit better. In pre-cal, we learned that the symbol for an inverse of f is denoted f negative 1 of x. That negative 1 is not an exponent. That negative 1 is a symbol to denote the inverse, okay? So some generic properties of inverses. If g is the inverse of f, then f is the inverse of g, so it works both ways. We know also from pre-cal that the domain of the inverse becomes the range of f, and the range of the inverse becomes the domain of f. Last, finally, it's important to note that not every function has an inverse, but if a function does have an inverse, this inverse is in fact unique. Okay, so we're going to explore the implications of just what you learned in pre-cal first before we do any calculus. So we're not even going to do any calculus yet. We're going to go right to a pre-cal problem. So we're going to start with the function square root of x minus 1. Okay, so part A asks us to find the inverse of f. So remembering that f of x is, we're going to rewrite as y is equal to the square root of x minus 1. In pre-cal, we learned that we're going to swap x and y. Because if we're reflecting this thing, then the x's become y's and y's become x's. And now we're going to solve for y. So I will square this side and square this side, giving me x squared is equal to y minus 1. I'm going to add 1 to this side and get y is equal to x squared plus 1. That's our inverse, but we're not going to write it like that. Our inverse, symbolically, is now x squared plus 1. Number 2, the second thing I want to do is actually graph these. So we can make a sketch of this. We all were really excellent in Algebra 2, so we can make a sketch of these two graphs. So we're going to have a set of axes, and we know that x squared plus 1 is the parabola parent function moved up 1 unit. And then we know that square root of x minus 1 is the square root function moved to the right 1 unit. And so some interesting things happen because we possibly have some domain restrictions here. So maybe we only need to include half of this parabola, and I'll explain why. Just half of this parabola, and we'll kind of dot this to show this here. And let's label them f inverse of x, and let's label this one f of x. And so in part C, it asks us to describe the relationship between these two graphs, and I hope that you can see that they are in fact reflections. F inverse of x is a reflection of f of x over the line y equals x. And we can see that line right here, y equals x. And so finally, we got to talk a little bit about domain. So in part D, it asks us to state the domain and range of f and f inverse. So important. starting with the function f, which is our original function. For f, it has a domain that is defined from 1 to infinity only. And its range is defined from 0 to infinity. Now, this is important because when we go to graph to describe the domain and range of f inverse, remember that the domain of f becomes the range of the inverse, and the range of f becomes the domain of the inverse. And let's look at that graphically. So our domain and range of the inverse, I can see that my range is supposed to start at 1 and go to infinity. And we're only going to capture from 0 to infinity on the domain here. And here's why. So this domain becomes the range, and this range becomes the domain, which is why we don't include this part of the parabola, because there's going to be domain restrictions. Okay? So how does this affect us in calculus? Why do I care about inverses? So we want to be able to take derivatives of inverses. So we're going to do a little bit of an exploratory exercise here. So we know that a function, x cubed, has an inverse of cube root of x. We know that, okay? So let's start by finding f of 2. So f of 2 would be 2 to the third power, or 8, okay? And I could also find the derivative of f of x, which would give me 3x squared. And I could find f prime of 2 by going 3 times 2 squared and get 12. Okay? Let's do the same thing with f inverse. So now I'm going to plug in f inverse. We're going to plug in 8 into f inverse. So we'll do the cube root of 8 and get 2. What is the derivative of f inverse? And so we're going to introduce some new symbols here, important. This symbol here is the derivative of the inverse. And so because there's that -1 symbol, we put a parentheses around it and a prime, okay? So we're going to take the derivative of cube root of x, just like we would know how to do 1/3 x to the -2/3 power, which we'll write as 1/3x to the 2/3. And then let's also plug in 8 into this function. So let's plug in 8 into the inverse, 3, and 8 to the 2/3 power. So cube root of 8 would be 2, and 2 squared would be 4, so 3 times 4, and we get 1/12. Now, it is not a mistake that this derivative is 12, and this derivative is 1/12. But notice they're not for the same value. This is the derivative for 2, and this is the derivative of the inverse at 8. And there's a special relationship between 2 and 8. In fact, f of 2 is 8, and f inverse of 8 is 2. And so we notice that f prime of 2 and f inverse prime of 8 are reciprocals. So this brings us to a theorem, the derivative of an inverse function. So let f be a function that is differentiable on an interval I. If f has an inverse function, which we'll call g, then g is differentiable at any x. And g prime is such that it will be 1 over f prime of g of x. And so if you were like me, you're looking at this and going, what? So let's write it down in symbols we know. If I want the derivative of an inverse function at a value a, we will go 1 over f prime of f inverse of a. okay? So here's why it's written a different way. If f of g of x is x, because they're inverses, okay? What if I took the derivative of this using chain rule? It would be f prime of g of x times g prime of x. Let's say I also take the derivative of this, which would be 1, okay? F prime of g of x times g prime of x, okay? If I solve this for g prime, I'm going to get 1 over, and when I divide the f prime of g of x to this side, that's where this formula comes from. But my preference is to actually use the formula that is listed out to your left. So this is kind of ugly to look at, and one of those things that is super easy, okay, super easy, that we often forget about by the time the AP exam rolls around, but it is a simple, simple concept, okay? So here's what it says. First example says f of 3 is 5 and f prime of 3 is 7/2. Find f inverse of 5. So we need to start by making some declarations here, okay? We know that f of 3 is 5. This means that f inverse of 5 is 3. So that's the first thing that's really, really important to understand here, okay? We also know that f prime of 3 is 7/2, okay? So we're going to go and we want to find f inverse prime of 5. So we're going to fill it in using this formula right here. So we're going to fill it in. It should be 1 over f prime of f inverse of 5. Okay? We know what f inverse of 5 is. We wrote it right here. F inverse of 5 is 3. And then we want to find f prime of 3, which we already have. So this becomes 1 over 7/2, or 2/7. And that's how we do our answer. Okay? Let's do it again. In this example, we're not given all of the pieces. So we're actually going to need to find f inverse of a and f prime of x before we can actually use the formula. So you're only going to be given f of x. So we need to start in this next problem. We need to use the formula as our guide. So f inverse prime of 2 needs to be 1 over f prime of f inverse of 2. So that's our formula, okay? So in order to do this, we need to figure out what is f inverse of 2. Now remember, if we're saying f inverse of 2, that means that there was some value when I set my function x cubed plus 2x minus 1, it had to equal 2. Because if this is an x value on the inverse, it's a y value on the original function, okay? So solving for this x value, we get minus 3, which will factor, which is solved by x equals 1. So x equals 1 would give us this value. So f inverse of 2 is in fact 1. Now you might go, well, why? That's true because f of 1 is 2. You see how this works back and forth? F inverse of 2 is 1 because f of 1 is 2. So we're going to it has to swap the values like that, okay? Now in order to execute this formula, we need to also find the derivative. So we're going to take the derivative and get 3x squared plus 2. So now we're going to look at our formula. In the inside of our formula, I see f inverse of 2. So this is going to become 1 over f prime. And instead of f inverse of 2, we now know f inverse of 2 is 1. So 1 goes there. Well, now this is easy because I just need to find f prime of 1. So we're going to our f prime. F prime of 1 is 3 times 1 squared plus 2, or 5. And so now we get our answer of 1/5. So I used my formula to guide my work here. Let's do it again. So g of x is equal to the square root of x plus 1. The square root of x plus 1. I want to find g inverse of 2. So start with your formula. G inverse prime of 2 is going to be 1 over g prime of g inverse of 2. So the first thing I know immediately that I'm looking at is I need to find g inverse of 2. Okay? So if 2 is the x value on the inverse, it's the y value on the original function. So I'm going to take my original function and I'm going to set it equal to 2. I'm going to square both sides and get 4 and find out that x equals 3. So it's important that you understand the relationship here. This means that g of 3 is 2. Therefore, g inverse of 2 is 3. So when I go over to my formula, instead of my g inverse of 2, I'm going to go ahead and slap the 3 right there. Okay? So now it's easy because I just need to find my derivative and plug it in. So my derivative, g prime of x, we're going to use a chain rule, 1/2 x plus 1 to the negative 1/2 power times the derivative of the inside, which is just 1, which we'll write as 1 over 2 square root of x plus 1. And my formula says I now need to find g prime of 3. So we're going to plug in 3 into this derivative. G prime of 3 is 1 over 2 square root of 3 plus 1. Square root of 3 plus 1 is 4. 2 times 2 is 4. And so now I've got 1 over, and we're going to plug in 1/4 for a final answer of 4. So I'm literally letting my formula guide me. I want you to press pause now and you try the bottom one. Give it a go, see what happens, okay? So if you've pressed play, you are now complete. I've got f inverse prime of square root of 3 over 2. So we're going to write our formula. 1 over f prime of f inverse of root 3 over 2. So I need to find this first, f inverse of root 3 over 2. So if it's an x value on my inverse, that means it's a y value on the original function. So we're going to go over here and we're going to set our function equal to square root of 3 over 2. So we know that cosine of x is equal to root 3 over 2 at pi over 6. So here's what that tells me. If f of pi over 6 is equal to root 3 over 2, then that means that f inverse of root 3 over 2 is pi over 6. So I'm going to my formula, and I'm now going to write 1 over f prime, and I'm going to substitute in pi over 6 for my f inverse of root 3 over 2. So now we got to find a derivative. We find our derivative. Let me get a different color. F prime of x, the derivative of cosine is in fact negative sine. And my formula says I need to plug in pi 6 into it. So I'm going to do exactly that. I'm going to plug in pi 6 negative sine of pi over 6. And I'm going to get negative 1/2. So now my final step is I'm going over to my formula. And I've got 1, and where f prime of 6 was, I'm now plugging in negative 1/2 for a final answer of -2. Now, a question students are always asking me at this point is, Miss Lowry, why can I not just find the inverse and take the derivative of that? You could, but in some of these, we don't know the derivative formulas yet, and this is actually sometimes faster depending on how complex the function is. So that's where I'm going to stop. We'll come into class, we'll do even, odd, or neither, and I'll see you guys next time.